Hey everyone. In this video, I'm going to talk about the basic idea behind hypothesis testing. Okay? So to provide a brief overview in the beginning, the underlying idea behind hypothesis testing is that it's a probabilistic proof by contradiction. So ultimately what we're doing with hypothesis testing is we assume the negation of the proposition and show that it leads to contradiction. Okay? So in other words, we're examining under a scenario where a given hypothesis would be true, how likely is it that we observe a given sample that we're observing, okay? So what this always involves is we construct what is called a null hypothesis, and this is this assumption, this hypothesis that we assume to be true for the data generating processes, as well as an alternative, which is sometimes called H1 or HA, but it's the alternative hypothesis to the null hypothesis. Okay, then we pick a test statistic T, and this is a statistic that we compute based on our sample. Okay. Then the next step is we figure out the sampling distribution of T under H0, which is sometimes also referred to as the reference distribution, right? And again, think about this in the context of the previous video where we talked about the sampling distribution as the distribution across repeated data generating processes, right? So we're assuming the null hypothesis is true, and then we're specifying the sampling distribution of T under the null hypothesis, and then examining, ultimately, lastly, whether the observed value of T that we have for our individual sample, that we collected, was this value of T likely to occur under the assumption that the null hypothesis was true, okay? And that's this probabilistic proof by contradiction. If the observed value was likely to occur, given that the assumed null hypothesis was true, then we have to retain our H0. If the observed value of T in our sample is unlikely to occur under the null hypothesis, then that leads us to reject the null hypothesis. Okay, and of course this sounds somewhat abstract. That's the underlying idea behind any hypothesis test, but in order to kind of provide a more concrete example, I'm going to go through one of the examples that is discussed in the book, and that I really like, and that example concerns predicting soccer matches, particularly in the context of the 2010 World Cup. And one famous prediction of these soccer matches that was actually widely reported, particularly in Germany, was POL the octopus. POL the octopus predicted soccer matches prior to the match, predicted the outcome of matches by basically having two boxes with treats in his aquarium, and then depending on which treat he would go for, that would decide which team won the match. Of course, you see here Germany and Spain in this specific prediction, and what POL did was before every game that Germany was involved in, basically predict the winner based on these treat boxes in the aquarium, and it turned out that out of the 8 matches that were predicted in the 2010 World Cup, each and every one of them was correctly predicted by POL the octopus. Okay, so up to the finale, Netherlands versus Spain, where of course Spain won the World Cup. All of those were correctly predicted by POL. The question, though, of course, is: did POL the octopus just get lucky, or does POL actually have some skills or some prophetic abilities to predict soccer match outcomes? And of course, the null hypothesis here in this context would be that POL is randomly choosing the winner, right? POL obviously doesn't really, follow soccer all that much, or doesn't have any idea of what is going on beyond the fact that he wants a treat, and just chooses one of them randomly, okay? So that's our null hypothesis. The test statistic in this context is the number of correct answers that POL the octopus gave in the context of the 2010 World Cup. And our reference distribution, so that's the distribution of this test statistic under the null, assuming that the null hypothesis is true, is a simple binomial distribution of size 8, because we have 8 individual matches, where the success probability, assuming that POL randomly chooses a winner, is 0.5, okay? So our reference distribution is a simple binomial of size 8, success probability of 0.8, okay? So now the question is, assuming the null hypothesis was true, what is the probability that POL gets all of these games correct, okay? Again, that's the underlying question. And of course, if we remember how to work with binomial distributions, that's fairly simple, a fairly simple question to answer, right? We can, of course, kind of hypothetically plot the underlying sampling distribution in the sense that we know exactly the shape of this binomial distribution. And I just plotted it here. You can see the code on RStudio Cloud to create this plot as well. Of course, this is centered at 4 because the success probability is 0.5. And we have a very small probability for assuming that the success probability is truly 0.5, a very low probability of observing 8 successes in a row. All right. We can also, of course, directly do this analytically. The probability of 8 correct predictions, assuming a success probability of 1/2, is just 1/2 to the power of 8, and that's equal to around 0.004. Okay. We can also compute the same probability in R using 2 different commands which are equivalent, and I just wanted to point both options out. One is dbinum, since the binomial distribution is a categorical random variable. Dbinum directly gives us the probability for that specific outcome. So dbinum 8, size 8, probability 0.5 is equal to 0.004, so exactly what we computed here. We could also do this with p-binum, which again gives you the probability, the cumulative probability up to a certain point, or if we include the option lower tail equals false, that's 1 minus that probability. So we have the probability of observing a value larger than 7, so that's just the value equal to 8, of a binomial distribution of size 8 with success probability 0.5, and of course that probability is the same value as the value up here. Okay. So okay. Oh yeah, and one note I should make is that of course in the group stage earlier in the World Cup, technically you could also observe ties. So of course, including possible ties, this probability would be even smaller because in addition to correctly predicting the winner, where you have 2 different choices, you have 3 different choices in any group stage match, and if each of those have the, or if each of those have the same probability, or you have kind of just randomly pick between those 3, that's one third to the power of 3 for 3 group stage matches, and so then the probability actually is reduced even more to 0.001, right? The key point here is what we did here is we computed our first p-value, which describes the probability that under the null you observe something at least as extreme as what you actually observed, right? So assuming the null hypothesis was true, how likely is it that we observe a test statistic that is equal to or larger than the test statistic that we actually observed? In our case, 8 successes out of 8 predictions, okay? And we see here, under the null, where the probability of a correct prediction is 0.5, that probability is incredibly small. It's 0.004 if we don't include ties, or 0.001 if we do include ties in the first round, or in the group stage of the World Cup. So that means in this specific scenario, based on the data that we have, we would reject the null hypothesis that Paul the octopus is only picking a winner by chance, because it's very unlikely that we would have observed 8 successes in a row given just a picking by chance. Of course, it's not that easy, and of course, ultimately, Paul the octopus just picked random winners, and we'll get to why that is the case. Okay. Just to go through another example, there were, of course, other animals that predicted games of the World Cup. For example, there was Manny the parakeet. Manny the parakeet was not as successful as Paul the octopus, as you can see here. Out of the I see that's 7 predictions, we only have 5 correct predictions and 2 incorrect predictions, and Manny did pretty well, but not quite as well as Paul the octopus. So if we go through the same calculations, the p-value is actually 0.0625 actually. Okay, but again, the problem here, or the thing that we have to keep in mind here, is that there were a lot of different animals that were, that had YouTube channels and predicted soccer matches, and this kind of relates to a broader problem in society, in science as a whole, which is the danger of multiple testing. The underlying idea here is, of course, that if you have 10, 15, 20 25 different animals that predict soccer matches, you're ultimately at some point bound to find one that correctly predicts all 8 soccer result, or all 8 World Cup matches, right? So for example, take 10 animals with no forecasting ability, and you can compute the chance of getting a p-value less than 0.05, which is usually our threshold to reject null hypotheses. So what is the chance of getting a p-value less than 0.05 at least once if you have 10 animals with no forecasting ability? And it turns out that that probability is that's just 1 minus 0.95 to the power of 10. So that's just one, at least one animal getting a p-value of 0.05, and that probability all of a sudden is 0.4, right? So as soon as you have, if you do this forecasting exercise with enough animals, you will find another Paul that correctly predicts all matches, right? So this might seem like a silly example, but it really kind of conveys key points that are true for social sciences, or sciences in general as well, right? Because there are a lot of different ways to test our hypothesis, a lot of different model specifications, a lot of different comparisons that we can make. And just as we can, look at 10 different animals and their predictions, and then just pick the one that have that basically has all correct predictions, scientists have to be aware that if they make a lot of different comparisons, they can run into the same problem. And so ultimately, having multiple tests and multiple comparisons that are essentially equivalent with regard to the underlying theory runs into this issue of multiple testing, and ultimately what it does is it inflates your underlying p-value. It increases the likelihood that you just by chance reject your null hypothesis. So this is a really important point that is kind of illustrated by this silly soccer example. Anyway, this is the first kind of illustration of the idea of hypothesis testing. The underlying structure is always the same. I'm just going to go back to this in a second. The underlying structure is always the same. We construct a null hypothesis and an alternative. We pick a test statistic, t, then we figure out what the distribution, the sampling distribution of that test statistic t is under the null, and that's what we call the reference distribution. And then we check in our sample, the one sample that we observed, how likely would it be to observe the t that we computed under the null hypothesis, under the assumption that the null hypothesis was true. And then if our t is very unlikely, just like, you know, Paul the octopus predicting all 8 matches correctly, then we're willing to reject our null hypothesis. Okay, and that's the essential basic idea behind hypothesis testing. Okay, I'll take a break here because we're already at 16 minutes. But in the next video, I'm going to continue our conversation about hypothesis testing, particularly in the context of proportions.